Hi everyone, welcome to this talk. Today I, Divya Bajaj, will present a new notion of traces and we'll see how we can transform these traces to generate explanations for programs. We all know that programs have to be correct and efficient, but programs also need to be understandable, especially in the case when you want to debug or maintain a program. Program explanations can also play a vital role in educational settings. So let's see how we can generate program explanations. The outline of today's talk is, first of all, we'll start by defining what is a trace. Then I'll present an object language. After that, we'll see how we can transform proof trees to generate these traces. These traces can become very huge, and so we'll see finally how we can simplify these traces using a query language to generate explanations. So let's start by defining what is a trace. A trace is a proof tree, except that it is a tag, that is, it shares equivalent nodes. So here the nodes G are shared among two parents and the second instance is given as a reference. Our traces do not include environments but instead binding nodes. Here the node H is a binding node for the variable F. Certain parts of the trace are elided using ellipses, like over here the nodes A and L. And finally, complicated function definitions are replaced by their names. Like over here in node H, the definition of factorial is replaced by the name fact. Let's see how we can generate such traces. Let's start by presenting an object language. An object language presented here is the extension of the untyped lambda calculus. The expressions in this object language evaluate to named values. Now, what is a named value? A named value is a plain value attached to the sequence of names. So a named value new is a plain value v attached to the sequence x1 to xk, where x1 is the first name that is attached to the value. Names are attached to the value using the var rule in our semantics. We are all very much familiar with the var rule of the standard call by value semantics. Here, when we look up for the variable binding of variable x in the environment row, we get a plain value v. In contrast to that, when we look up for the variable x in our environment row, in our semantics, we get the named value. Also, the name x is attached to the named value to the right. We call our semantics call by named value semantics. Now, why do we use named values? Let's look at the explanation for twice factor. Over here, the left trace uses plain values, whereas the right trace uses named values. If we look closely, the expression twice fact in the node C evaluates this abstraction lambda x to f applied to f of x, which in turn leads to node D containing the expression f applied to f of 2. Whereas if we use named values, the expression node D is fact applied to fact of 2. So because of using plain values, we have this reference f as an alias for fact. This can provide an indirection to the user and which can lead to confusion. Also, when the reference f is applied to the value 2, the reference f is substituted by the value of factorial, which does not happen in named value case. So when this f is substituted by the value of factorial, this can create a much more complicated trace. However, when we use named values, we substitute the complicated values with names, and so we have much more simpler traces by using named values. Now, we all know that proof trees can be considered as a declarative view of our for the execution of a program. So if we look over here for a proof tree for the program square root of 5, we see that we have these nodes h and I and k and l equivalent. Also, we have environments in our nodes. So to go from proof trees to traces, we want to share our equivalent nodes and we also want to remove the environments. Let's look at it step by step. Sharing equivalent nodes. So in the trace on the left, we have these nodes h and I equivalent and also the nodes k and l are equivalent. So sharing equivalent nodes is simply done by removing the second instance of the equivalent nodes. If that second instance would have been a child for a different parent, then we would have a reference to the equivalent node like we had for reference for G in twice fact. Here we simply just remove it. Now, second step is removing environments, which is not very simple. So if we look at the node C, the binding square, if we remove that, we lose two things. We lose the immediate information regarding the value for the binding of square, and also we lose the information regarding where the binding for square is visible, like the scope of the binding. And so to overcome these things, before removing environments, first of all, we tag our bindings with origin scope pairs. Secondly, we replace variable lookups with binding nodes. So let's start by tagging bindings with origin scope pairs. So if you look at the binding for square in C, this is originated by the let rule in our semantics from node A, and the scope is in the subtree with the root C. And so we tag our binding for square with A dot C. Similarly, for the binding of X, we tag it with C dot F. So now we have the information regarding the origin and scope of each binding in all of our nodes. Finally, we can replace our variable lookups with binding nodes. So if you look at the variable lookups in D and G, this can be replaced by the binding node in D on the right side. The binding node stores information regarding this variable square bound to a value and the origin and scope being A and C. It still shows the complete information, but is much more simpler. Similarly, we can replace the variable lookup in H and K by the binding node in H. So now, because we have our binding nodes that store the information regarding scope and the value of the variable, we can simply remove environments from all of our nodes in the trace. That is, C and F the environments are just removed from the nodes C and F. So we know we have defined what a trace is. A trace that shares equivalent nodes. It doesn't include environments but includes binding nodes, and also complicated function definitions are replaced by their names. So we have talked about these three things. What we haven't talked about is how certain parts of the trace are elided using ellipses. First of all, why do we need to do that? We need to do that because a complete trace can become very huge, which we will see later on in one of the examples. And we need to simplify these traces for an explanation. This is done by transforming these traces, and certain parts of these traces are then elided using ellipses. So how do we do that? We do that using a set of operations that we have defined, and then we'll also define a query language that applies these operations as transformations on our traces. So let's start by defining these operations first. We have the hiding nodes operation. The hiding nodes operation simply, just as the name suggests, hides the nodes in our traces. Applying judgments operation. This is a much more complicated one. In this, we propagate the value of our judgments to the other parts of the trace, and finally we can combine these two operations and give a factoring subtraces operation, where we apply the judgments as well as hide the nodes. So let's look at each of them one by one. Let's look at hiding of nodes. So on the left side, we have a trace for the program that checks if 3 plus 6 is an even. If we look at the node C, that shows the computation for 3 plus 6 equivalent 9. And this can be considered a very trivial computation. And so we may not want to keep this in our explanation. We can simply hide this by replacing this with ellipses. Now, why do we not just simply remove nodes, and why do we replace them with ellipses? This is because if, say, we remove the node C, then the nodes E, F and G would now become the children of node B, which would make the trace incorrect. So if a node that is hidden has non-hidden children, we just replace it with ellipses. Otherwise, we would have hidden the node. Now, if you look on the trace on the right side, we have removed the computation 3 plus 6 equivalent 9. We have hidden it from our trace, but node B still contains the expression 3 plus 6. We also want to replace this with 9. How do we do that? This is done using the applying judgments operation. So now if, say, we, instead of hiding the node C, we apply the node C, that will just replace the expression 3 plus 6 with 9 in the node B. Now if we look at the trace on the right side, this trace is an explanation for if 9 is an even number or not. So the subtree with root C, that is 3 plus 6 equivalent to 9, becomes redundant. It is not relevant anymore to this explanation, and so we should also remove this. So we never simply apply a judgment. We always factor these subtraces. That is, when we say we want to propagate this judgment to other parts of the trace, we also want to hide that subtrace. This is done using the factor operation. So when we factor the node C, we substitute the expression 3 plus 6 by 9 in node B, and also hide the subtrace with the root C. So the root C, E, F and G are hidden. So we have defined three operations here: hiding of nodes, applying judgments, and then the combination factoring subtraces. Now, how do we apply these operations on our traces? This is done using filters. Now, filters are defined as queries. Now, what is a query? A query consists of two parts, operation and pattern. Operations, as you have defined already, are hide, apply, and factor. They define how our traces are transformed. That is, do we want to hide a node, do we want to propagate the values of the judgments, or do we want to do both the things, that is factor the subtraces. The pattern part of the query defines where this transformation is to be applied, that is, on which particular nodes. So let's say, for example, the reflexive pattern that will select all the nodes containing reflexive judgments of the form, say 3 evaluates 3, and this is defined using such a pattern. So let's see how can we apply our queries on traces and apply transformations on traces really. So let's take the same example here. If we look at nodes E, F, I, and J, these nodes consist of reflexive judgments and did not contribute to the explanation. One way to hide them is to apply the hide operation 4 times. That is hiding nodes E, F, I, and J individually. But we can do it much more efficiently using queries. The query that we can use over here is hide reflexive. The reflexive pattern will select the nodes E, F, I, and J, and the hide reflexive will hide all the nodes that are selected by the reflexive pattern. And so when we apply this query on our trace, the nodes E, F, I, and J are hidden from the trace. So now we have the tools to transform our traces. Let's see how these transformations or how explanations are generated on a much more complicated example. Let's take a factorial example, like to find the factorial of 6. The complete trace really looks like this. That's what we said. A trace can become very huge and we want to simplify it, because if you look at this complete trace, it is really unreadable and no one can make out what is going on over here. So we want to apply some transformation on these traces to generate an explanation. Now, one such explanation can be the one that is over here on the left side. What you see on the right side is kind of like a user interface. In our prototype, we have defined a set of patterns, and the user can select if they want to hide using that pattern, factor using that pattern, or maybe just not apply any operation using the pattern. So here we hide all the top level declarations, we factor all binding nodes, we factor all the decrements, say 6 minus 1, we hide reflexive judgments, we hide pattern match judgments, and a lot of other things. But we do not want to, the user does not want to hide or factor case expressions. They want to keep the case expressions or the multiplication judgments. Now, this is a good explanation for a particular user. However, for maybe other users, these case expressions are just too much and they're trivial for them, and they're like, I don't want these case expressions. So another user can simply just hide these case expressions, and this is another explanation. So what we can see over here is that these explanations are user controlled. A user has complete control over what is to be included in the explanation and what is not, and that makes it a lot more flexible. Because for two different users have a different level of expertise, and so what can be trivial for one user may not be trivial for another user. And so our approach provides that flexibility and that complete control to the user to what to include in the explanation and what not to include in the explanation. So what we saw over here is that proof trees can be considered as a basis of explanations. Secondly, we can define filters using our query language, and these filters can be applied on traces to simplify these traces, and this can result in explanations. Third, these explanations are user controlled. That is, a user can decide what to include and what not to include in an explanation. So a user has complete control over what an explanation will look like. Finally, we discussed a lot of applications for program explanation. That is, these explanations can be used for maintenance work, debugging, and also in educational settings, like we saw in the examples for Factorial and twice fact. Factorial is a very nice example to understand recursion, and so these explanations can be used to understand recursion and a lot of other things in educational settings. Thank you.